Are turbocharged cars really better than NA ones? The primary difference between normally aspirated NA and turbocharged engines is how they compress and intake air. By compressing air before it enters the cylinders with a turbine powered by exhaust gases, a turbocharged engine boosts power and efficiency from a smaller engine size by enabling more air and hence more fuel to burn. A naturally aspirated engine, on the other hand, uses no forced induction and only atmospheric pressure to pull air into the engine. Preferences regarding power, efficiency, upkeep, and driving feel will determine which option is best. Here are 8 key points comparing them. Number 8. Power output. By compressing intake air before it enters the combustion chamber, using a turbine driven by exhaust gases, turbocharged engines take advantage of the basic principle of forced induction. The air's density is greatly increased by this compression, enabling a larger mass of oxygen molecules per unit volume inside the cylinder. This allows turbocharged engines to inject and burn more fuel every cycle, significantly improving power and torque outputs without increasing engine displacement, since combustion efficiency is dependent on the amount of oxygen available. A 1.5-liter turbocharged engine, for instance, can generate power that is on par with or more than that of a 2.5-liter naturally aspirated engine, which is dependent only on atmospheric pressure to fill its cylinders. Because naturally aspirated engines rely on the piston-induced vacuum to draw air in, their maximum volumetric efficiency is physically limited to between 85 and 95%. Number 7, fuel efficiency. Because turbocharged engines allow for significant downsizing, small displacement engines run at ideal loads and RPM for everyday driving while preserving high-power reserves under boost conditions. They often achieve superior fuel efficiency on a power-to-power basis. Smaller engines lower pumping losses and decreased internal friction, contribute to fuel savings when driving normally. Crucially, turbos operate on demand, enabling the engine to run at low boost or under naturally aspirated conditions while cruising, improving part load economy, and triggering higher boost when necessary full throttle or heavy load. Number 6, throttle response. Because of the direct airflow correlation with throttle opening, the piston draws in air as soon as the throttle opens. Without any intermediate processes, throttle response in naturally aspirated engines is almost instantaneous. This makes it possible to precisely modulate power, which is very useful for low-speed maneuvering and performance driving. The main cause of turbo lag in turbocharged engines is that the turbine requires a certain amount of exhaust gas flow to spin up and produce compressed intake air, which usually results in a delay of less than a second. Although lag has been greatly reduced by innovations like electric assist turbochargers, variable geometry turbines, and twin-scroll turbos, some delay is still noticeable. Driver confidence and the sense of immediacy may be impacted by this latency. Furthermore, in order to control power delivery smoothness, turbocharged engines frequently use more intricate throttle mapping and boost controllers, which, despite their sophistication, are unable to completely duplicate NA linearity. Number 5, reliability and maintenance. Because naturally aspirated engines have fewer parts, including wastegates, intercoolers, high-pressure fuel systems, turbochargers, and intricate cooling circuits, they are more mechanically reliable and require less maintenance. Engine components experience reduced mechanical and thermal stress when there are fewer parts, which also reduces the number of possible failure spots. The high rotational speeds, typically over 100,000 RPM, and severe heat exhaust gases can reach 700 degrees Celsius, required for turbocharger operation, necessitate careful cooling and lubrication failure, or wear of turbo components can result in costly repairs and possible collateral engine damage. In addition to requiring stronger pistons, rods, and cooling systems, the increased thermal stress also raises the cost and complexity of the engine's internal components. However, with the developments in electronic controls, bearings, ceramics, and metallurgy, current turbo systems now have far longer lifespans. For lifespan, proper maintenance schedules are essential. Number 4, driving feel. As the turbo spools, turbocharged engines produce strong and occasionally abrupt power surges that are frequently apparent as a quick surge or kick following first throttle application. This feature, which amplifies acceleration at mid to high RPM, can produce an exhilarating driving experience. particularly in sporty or performance-oriented cars. It may be necessary to acclimate and carefully modulate the throttle in spirited driving or low-grip situations due to the nonlinear power delivery, which causes the throttle to feel less responsive at first and then abruptly forceful. Natural aspirated engines, on the other hand, provide a more gradual and linear rise in power from idle to redline, which translates into predictability and ease of throttle modulation that is advantageous for precise driving, such as on a racetrack or in tricky driving situations. Purists frequently favor the tactile and oral characteristics of revving NA engines because of their connected and mechanical feel. Number 3, performance at high altitude. Air pressure and oxygen content drop as altitude increases, reducing combustion efficiency and engine power. Naturally aspirated engines suffer directly from this because they rely solely on atmospheric pressure to fill cylinders. As air gets thinner, less oxygen is available, causing a significant drop, often 3% loss in power per 1,000 feet altitude. Turbocharged engines counteract this loss by compressing intake air. Number 2, cost. From an initial purchase and manufacturing perspective, naturally aspirated engines are typically less expensive due to their mechanical simplicity, fewer parts, less sophisticated cooling and lubrication demands, and simpler engine management systems. This translates into lower labor and parts costs for repairs and maintenance over the vehicle's life. Turbocharged engines require additional components: turbocharger unit, intercooler, wastegate, upgraded fuel system, reinforced internals, necessitating more complex design, assembly, and calibration. Number 1, emissions. Turbocharged engines generally excel at reducing emissions per unit of power generated by improving the combustion process. Forced induction enables more complete and efficient burning of fuel by increasing combustion chamber air density, reducing unburned hydrocarbons and carbon monoxide. By optimizing fuel-air ratios under varying loads, turbocharged engines enable automakers to meet increasingly stringent emissions regulations globally, with smaller displacement engines producing equivalent power, helping lower CO2 output. In summary, turbocharged cars are generally better for power and efficiency, especially in smaller engines and high-altitude conditions, but they come with considerations like turbo lag, complexity, and maintenance. Naturally aspirated engines excel in reliability, linear response, and simplicity, making the best choice dependent on the driver's priorities and usage. If you liked our video, please hit the like button and subscribe to our YouTube channel.